Every time you climb a flight of stairs, your body performs a specific, measurable quantity of physical work against the gravitational field of the Earth. This is not a metaphor, and it is not an approximation. Work, in the physics sense, is force multiplied by displacement in the direction of that force. And when you climb stairs, you are lifting your entire body mass vertically upward against a gravitational acceleration of 9.8 meters per second squared, step by step, with every single repetition. A 70-kilogram person climbing 10 meters of vertical height performs approximately 6,860 joules of mechanical work against gravity, every single time they make that climb, regardless of how slowly or quickly they do it, regardless of how tired they feel, regardless of how much they would prefer to take the elevator. The physics is indifferent to preference. The work is real, it is quantifiable, and crucially, it must be performed entirely by the biological machinery inside your own body, which means every one of those joules is paid for by metabolic processes running inside your cells, by muscles contracting under load, by a cardiovascular system mobilizing to deliver the oxygen and fuel that those contracting muscles demand. This is the foundational reason stair climbing is as physiologically significant as it is, and it distinguishes it mechanically from the activity it most superficially resembles: flat ground walking. When you walk on a level surface, your center of mass does oscillate slightly upward and downward with each step, but the net vertical displacement across the full stride cycle is approximately zero, because the slight rise at push-off is recovered by the slight descent at heel strike in a pendulum-like exchange of potential and kinetic energy that dramatically reduces the net metabolic cost of horizontal locomotion. This pendulum mechanism is one of the most elegant energy conservation features in human bipedal gait, reducing the metabolic cost of walking to a fraction of what it would be if you had to power every step entirely from muscular effort. It is also entirely absent in stair climbing. On stairs, your center of mass does not return to its previous height after each step. It moves upward and stays upward, stair by stair, because you are literally ascending, and every unit of potential energy gained is paid for by muscular contraction rather than recovered from the kinetic energy of forward momentum. There is no pendulum energy exchange available to subsidize the cost. Every step is a net energy expenditure. Every step requires your muscles to produce enough force to lift the entire weight of your body from one stair to the next, without the energy recovery assistance that makes flat walking so comparatively efficient. This is why a flight of stairs that takes 30 seconds to climb produces a cardiovascular and metabolic response far more intense than 30 seconds of flat ground walking at a brisk pace. The physics of the task, specifically the net vertical work required, simply costs more. The muscle recruitment pattern activated by stair climbing reflects this elevated mechanical demand and differs from flat walking in specific, well-characterized ways. The primary drivers of stair ascent are the large muscles of the lower extremity, the gluteus maximus, the quadriceps femoris, and the soleus and gastrocnemius muscles of the calf, all working together in a coordinated sequence timed precisely to the mechanics of each step. As your lead foot lands on the riser above you and accepts the full weight of your body, the gluteus maximus and quadriceps are required to produce hip and knee extension against gravity under load, generating the force that propels your center of mass upward to the height of the next stair. This is a concentric contraction, the muscle shortening while producing force, and it is mechanically demanding in proportion to the weight being lifted, which is your entire body mass. But the muscle story of stair climbing does not end with the concentric push. As your trailing leg follows and your weight transfers forward, the quadriceps of the leading leg must control the rate of knee flexion as the body's center of mass descends slightly relative to the next step, performing what is called an eccentric contraction, the muscle lengthening while still under tension, acting as a brake against gravity rather than a driver against it. Eccentric contractions are a defining mechanical feature of any movement involving controlled descent against gravity, whether that is the downstroke of a bicep curl, the landing phase of a jump, or the transition between stair steps, and they carry a specific physiological consequence that makes them considerably more significant to long-term adaptation than concentric contractions alone. At the level of the individual muscle fiber, eccentric loading produces a pattern of mechanical stress, fundamentally different from the stress generated during concentric shortening. When a muscle fiber is required to generate force while simultaneously being stretched, the sarcomere, the basic contractile unit of muscle, composed of the interdigitating actin and myosin filaments we explored in earlier discussions of muscle physiology, experiences a type of mechanical strain that disrupts the regular lattice structure of its contractile proteins more extensively than concentric contraction typically does. At the cellular level, this manifests as microscopic disruption to the sarcomere structure, visible in electron microscopy as Z-line streaming, a blurring and distortion of the regularly spaced structural boundaries that separate adjacent sarcomere units along the myofibril. This microdisruption is not injury in the clinical sense. It is the specific mechanical signal that activates the most potent pathway for long-term muscle adaptation: satellite cell activation and myofibrillar protein synthesis. Satellite cells are muscle stem cells that reside between the sarcolemma and the basal lamina of muscle fibers, dormant under resting conditions, but activated in response to mechanical damage and the local signaling cascade it triggers. Following eccentric loading sufficient to produce meaningful sarcomere disruption, satellite cells proliferate and differentiate, contributing new myonuclei to the affected fiber. More myonuclei mean a greater capacity for protein synthesis within that fiber, because each myonucleus governs protein production within a limited domain of cytoplasm. More myonuclei mean more ribosomes translating structural proteins, more actin and myosin being synthesized, and ultimately a larger, stronger, mechanically more capable muscle fiber. This is the cellular foundation of muscle hypertrophy, and it is initiated more potently by eccentric loading than by concentric loading alone. Stair climbing. By incorporating both concentric drive on ascent and eccentric control on descent, delivers both mechanical stimuli in a single repeated movement pattern that requires no equipment and is accessible in almost any multi-story building anywhere on Earth. The metabolic cost of stair climbing sits at an intensity level that is unusual among everyday physical activities, and understanding why requires a brief look at how your body selects and depletes its energy substrates depending on the intensity of the demand placed on it. At rest and during low-intensity activity, your cells derive the majority of their energy from aerobic fat oxidation, a slow, high-yield process that produces large quantities of ATP per molecule of fat, but operates relatively slowly in terms of ATP production rate. As exercise intensity increases and the demand for ATP rises faster than aerobic fat oxidation can supply it, your cells progressively recruit faster but less efficient pathways, glycolysis, breaking down glucose rapidly but producing fewer ATP per glucose molecule. And at very high intensities, the phosphocreatine system we explored in earlier discussions of grip fatigue, providing an immediate but rapidly depleted source of ATP for maximal efforts lasting only seconds. Stair climbing, particularly at a moderately brisk pace, places muscular demand at an intensity level that pushes well into the glycolytic contribution zone for most people, while still relying substantially on aerobic pathways. This dual contribution to energy supply creates the specific metabolic signature characteristic of stair climbing: a rapid rise in oxygen consumption toward a high fraction of maximum aerobic capacity, accompanied by lactate accumulation in the working muscle reflecting the glycolytic contribution, and a sustained elevated heart rate and breathing rate reflecting the cardiovascular effort required to deliver oxygen at the rate the working muscles demand. Measurements of oxygen consumption during stair climbing, conducted in exercise physiology research settings, have consistently shown that stair climbing at self-selected moderate paces elicits between 60 and 80% of maximum oxygen uptake in healthy adults, a range comparable to what many people achieve during moderately vigorous aerobic exercise, and higher than most activities of daily living ever approach. This high fractional VO2 demand is important for two reasons. First, it means that even short bouts of stair climbing, lasting only 1 to 3 minutes, produce a meaningful cardiovascular stimulus in a very compact time frame. Second, it means that accumulated stair climbing across a day, even in short fragmented bouts, can contribute measurably to total daily energy expenditure and to the total cardiovascular training stimulus received in a way that low-intensity activity simply does not replicate. Research specifically examining the cardiovascular effects of stair climbing as a training intervention, including a frequently cited study from Queen's University in Belfast, examining the effects of a short stair climbing protocol performed in brief daily bouts on cardiorespiratory fitness in sedentary young women, found significant improvements in VO2 max, the gold standard measure of cardiovascular fitness, following the stair climbing intervention compared to control groups. Subsequent research confirmed these findings in broader populations and across longer intervention periods, establishing stair climbing as a genuine cardiovascular training stimulus rather than simply a more intense form of daily ambulation. The hormonal response triggered by the combination of muscular load and elevated metabolic demand characteristic of stair climbing adds another significant dimension to its adaptive effects. Resistance-style loading against substantial external force, in this case the force of gravity acting on full body weight, triggers the release of anabolic hormones, including testosterone and growth hormone, through mechanisms involving mechanoreceptors in muscle tissue, central nervous system responses to the exertion demand, and the metabolic stress signals generated by accumulated lactate and hydrogen ion concentration in the working muscle. Growth hormone, in particular, responds strongly to the combination of mechanical loading and metabolic acidosis that stair climbing produces, rising rapidly during and immediately following intense stair climbing efforts and remaining elevated for an extended post-exercise window that contributes to the tissue repair and remodeling processes initiated by the exercise bout. These hormonal responses serve as systemic amplifiers of the local cellular adaptation signals initiated in the muscle fibers themselves. Growth hormone promotes insulin-like growth factor 1 production in local tissues, which stimulates satellite cell activation and protein synthesis in muscle. It also stimulates osteoblast activity in bone, contributing to the bone remodeling response that makes stair climbing particularly valuable from a skeletal health perspective, a point we are about to examine in detail. Bone is often considered, incorrectly, as a fixed, static tissue in adulthood, an inert scaffold that simply holds everything else in place. Like muscle, bone is living tissue under continuous remodeling, governed by the same balance of forming and resorbing cells, osteoblasts and osteoclasts, discussed in the exploration of facial aging, and it responds to mechanical loading in a way that makes it directly sensitive to the kind of impact and compressive forces generated during stair climbing. Bone remodeling is governed by a principle called Wolff's Law, first articulated in the 19th century, which states that bone adapts its structure and density in response to the mechanical loads it habitually experiences. Regions of bone regularly subjected to high mechanical stress add mineralized matrix to reinforce their load-bearing capacity. Regions experiencing reduced mechanical loading lose density as the remodeling balance tips toward resorption. Stair climbing generates mechanical loading on the bones of the lower extremity, the femur, tibia, fibula, calcaneus, and metatarsals, that is qualitatively and quantitatively distinct from the loading produced by flat walking. Each step involves a brief impact transient as the foot lands, propagating a mechanical impulse upward through the skeletal chain, followed by a sustained compressive load as the weight-bearing leg supports and then propels the body upward. This combination of impact impulse and sustained compressive load has been shown to be a particularly potent stimulus for osteoblast activity, more so than the steady, lower-impact loading of flat walking, and research examining bone mineral density in populations with high habitual stair use, or in intervention studies using stair climbing as a specific exercise modality. has found associations with higher bone mineral density at load-bearing sites compared to more sedentary comparison groups. Among the most important long-term biological adaptations to regular stair climbing is one that happens not in the muscle fibers themselves, but inside them, at the level of a subcellular organelle most people learned about in biology class but rarely consider in the context of fitness: the mitochondria. Mitochondria are the primary sites of aerobic ATP production in your cells, converting glucose and fatty acids into ATP through the electron transport chain using oxygen as the terminal electron acceptor. The number of mitochondria per muscle fiber and the density of the enzyme complexes within each one is not fixed. It increases in direct response to repeated aerobic exercise stimuli through a process called mitochondrial biogenesis, the creation of new mitochondria from existing ones, driven primarily by a master regulatory protein called PGC1-alpha, whose expression in muscle cells rises in direct proportion to the exercise-induced signals of energy deficit, metabolic stress, and elevated intracellular calcium generated during sustained moderate to high intensity muscular activity. More mitochondria per fiber means a greater capacity for aerobic energy production, a higher ceiling for the rate at which your cells can regenerate ATP through oxidative pathways, and therefore a higher work rate your muscles can sustain before having to rely heavily on anaerobic glycolysis and its accumulation of fatiguing byproducts. This is, at the cellular level, what improved cardiovascular fitness actually represents. Not larger lungs, not a dramatically different heart, but denser, more metabolically capable muscle tissue, able to do more aerobic work per unit of time with less physiological disruption. Stair climbing, by repeatedly stressing the aerobic system of the large lower extremity muscles at a high fractional intensity, delivers a potent PGC1-alpha stimulus, and therefore a meaningful mitochondrial biogenesis signal, with each session nudging the mitochondrial density of the working fibers incrementally upward, accumulating across weeks and months of regular practice into a measurable increase in aerobic capacity. The cardiovascular adaptation, running in parallel with the mitochondrial and muscular changes, reinforces the cellular improvements through changes in cardiac output, stroke volume, and the efficiency of oxygen delivery to working tissue. Regular exposure to the elevated heart rate and cardiac output demands of stair climbing progressively increases the strength of the cardiac muscle, particularly the left ventricle, allowing it to eject a larger volume of blood per beat, reducing the heart rate required to deliver any given cardiac output, and improving the efficiency of oxygen delivery to peripheral tissues. This cardiac adaptation, known as cardiac hypertrophy in its exercise-induced, physiologically beneficial form, directly counterparts the skeletal muscle mitochondrial adaptation, together constituting the two major components of improved cardiorespiratory fitness. The clinical significance of cardiorespiratory fitness as measured by VO2 max cannot be overstated. VO2 max is now recognized as one of the single strongest predictors of all-cause mortality available in clinical research, with low cardiorespiratory fitness conferring a risk of premature death comparable to or exceeding that conferred by traditional major risk factors including hypertension, diabetes, and smoking. Research published in JAMA Network, open examining cardiorespiratory fitness and survival across large cohorts, has consistently found that improving from low to moderate fitness categories, a transition well within reach through sustained stair climbing habits, is associated with a larger absolute reduction in mortality risk than virtually any pharmacological intervention available for primary prevention. This is not a claim that stair climbing is a treatment for any condition. It is a statement about what the long-term accumulation of mitochondrial, muscular, and cardiovascular adaptation, produced by regular vigorous physical activity, does to the overall resilience and physiological reserve of the human body across decades. On the practical question of how much stair climbing is needed to produce meaningful adaptation, the honest answer from the research literature is that the dose-response relationship is favorable at surprisingly modest absolute amounts. Research examining stair climbing as an isolated intervention has found improvements in VO2 max and metabolic markers from protocols involving as few as 3 to 5 minutes of total stair climbing per day, performed in fragmented bouts across the course of normal daily activity rather than requiring any dedicated exercise session. The key determinant is not total duration, but intensity relative to individual capacity. The stair climbing needs to be performed at a pace that elevates heart rate meaningfully and creates a genuine metabolic challenge, not at an ambulation pace equivalent to flat walking. The physics guarantees a minimum work output per step regardless of pace, but the physiological adaptations responsive to cardiovascular stress require the intensity to be high enough to generate that stress. So here is the real reframe to sit with as we close this exploration. The flight of stairs in your building, your office, your home, your commute, is not an inconvenience to be managed or an obstacle to be replaced by an elevator whenever possible. It is a gravitational loading machine, a completely free, always available device that forces your body to perform real, quantifiable mechanical work against the fundamental force holding every object on this planet to its surface. Every step up is a unit of mechanical work performed against gravity. Every eccentric descent step is a microsignal initiating sarcomere remodeling and satellite cell activity. Every bout of stair climbing at a challenging pace is a PGC1 alpha stimulus pushing your mitochondrial density upward. Every session is a bone-loading event reinforcing mineral density at the most functionally critical skeletal sites in the body. Every accumulated hour of weekly stair climbing is a contribution to a VO2 max trajectory that the long-term mortality data identifies as one of the most powerful health investments a human being can make with the time available in an ordinary day. The elevator was invented to solve a problem. The problem it solved was not the mechanical work of climbing stairs. The work was never the problem. The work was always the point. What other ordinary physical challenge in your daily environment do you now see differently after understanding its underlying physics? Leave your answer in the comments below, and we may build the next episode directly around the mechanism hiding inside the movement you find most intriguing. Until then, keep questioning the things you assumed you already understood, because the most powerful biology in your own life is very often hiding in the things you walk past every single day.